Hi, so welcome back. So what we were basically positioned at is that we were looking at the boundary layer, and we said that the boundary layer profile at two x locations are similar to each other. And what do we mean by that? Is that basically we can superimpose the velocity profiles on each other, and therefore, for example, if you look at this diagram here, so the velocity profile at x4, I can get this, but by multiplying the entire velocity profile at x1 by a suitable scaling factor. If I do that, I should be able to get. So basically, just to give you a very crude example, say if I say multiply the velocity profile at x1 by say 2, then I should be able to get the velocity profile at x2. Maybe if I multiply it by 3.5, I should get at x3 and something like that. Okay, so that's what I'm trying to mean. Now, what we were just saying is that there is a certain momentum transport in the y direction. Now, why are we talking about this right now? Because we're trying to understand, see, these equations and these numbers and lots of things that we're writing also comes from the fact that we're trying to physically understand the flow, right? So we're trying to mix both. We can try to understand the physical process as it is happening, and then use quantitative mathematics to develop equations and solve them and all of that. Okay, now look at this, for example. So we said there is a certain momentum transport in the y direction, right? And we said the velocity of that, we're going to denote that as uv, okay, uv, and this is a function of kinematic viscosity and delta. So we don't know exactly what the function should be, what the scaling factor should be, but the dimensionally correct. So therefore, this is it's a possibility. Now, what we're going to do is, how is this happening? Like I said, there are these fluid particles which are, say, coming in. All right. Now, what happens? I mean, look at this, say at location x3, right? Now, what exactly is happening when these particles come here, right? Now, as these particles now say the particles are passing x3, okay? Now, the question is that what is the time taken, right, for the particle to cross this position at x3, right? And while it is doing that, during this time that it takes to go from 0 to x3, right, some particles have also moved away from the wall, right, because of the momentum transport, because the viscosity transports some momentum away from itself in the y direction, right. So these two things are happening at the same time, right. I think that makes sense. So that, and because in a way to look at this is that it's being sort of pulled along x-axis as well as pulled away, along the y-axis. So therefore, if there are certain the particles, the time that these particles take to go from the first from the edge or leading edge of the boundary layer to leading edge of the flat plate to say x3, to x3. And during that time, there are particles which are being transported away, right, into the y-axis. So it's the same time, right? Now let us see if I can put do a little bit of a quantitative analysis for that. So let me sort of write that down, and hopefully this makes sense to you, right? Now, let us look at this, the time required. So what I'm looking at is time required to move past, say, some x distance from the leading edge by a particle, right? The time required by a particle to move past some x distance from the leading edge, right? I'm going to call that as t1, okay? And the time required for momentum transport in the y direction is t2, right? Now, so what should be, so the time required to move past some x distance from the leading edge, what should that be? So if I said x3, so this is the x3, and what is the velocity with which, so this is the, the particle, in the normal case, what is the velocity which is required, right? What is the velocity with which it will require to move from, x direction, right? So this is basically, this is the total distance is x, and it is moving with free stream velocity. And that's the total time which will be required, right? Now, what is the time required for momentum transport in the y direction? So we said that the distance, right, there again, the time required. So the distance is delta, right, and the corresponding velocity is uv. Right? And then, so again, this is distance by velocity, and this is again distance by velocity, that gives you the time, right? Now, when I say that, now again, uv is something that we said we could write like this. So therefore, this ultimately becomes delta square by nu, right? So therefore, if I take, so basically what I'm saying is, so if I take a particle, right, so if it's the total time that will be required for the particle from going to here is basically free stream, right, and and during that time there is also a momentum transport in the y direction, which we are looking at like this. Right. So therefore, what we're saying is, if you look at this, so when we say the distance is delta, right. So we are looking just this distance delta basically means I'm looking at a particle just about at the boundary layer edge, right. That's why, so we have this particle which is moving in the free stream, and this is a particle which moves up by delta, right. So it's like, these two are kind of meeting each other. Right. So I have a particle, right, free stream, which moves along here, right, which moves along here, and it, at the time when it is at x3, right, it takes time t1, right, and this is moving with free stream velocity. It is at the distance, say x3. At the same time, there is this particle which is being transported from y is equal to 0 to y is equal to, say, delta, right, with a velocity uv, right. So, and this time is basically t2. Now, what we're saying is that t1 is equal to t2, right. So when I say that, so when I so that's what we get, right, and so then we set that, okay, and we say that t1 is equal to t2, right. If I do that, what do I get? So I get x by u infinity is equal to delta squared by nu, right, nu, or delta, which is a function of x, is equal to x nu by u infinity. Okay? This Okay. Now, what is interesting is, now we looked at this. Now, if you've not already noticed, now what we've done earlier is that delta by L, right, is a function of 1 by under root of RE. Okay. Now, in this particular case, okay, you replace here, you replace V, well, you know, because RE is V, okay, rho VL by mu. Okay. So, replace V by V infinity and L by X. Okay. So, I would like you to do this yourself, just cross check, just cross check, you know, do this and cross check and see. This is something that we had, you know, pulled up earlier, you know, what we saw, and this, we got this from another, you know, point of view, another way of looking at this boundary layer. Okay. So, tell yourself what this will come about. You know, this is something that you had looked at earlier. Okay. Fine. So, looked at that. Okay. So, now let us go back and say that we had this similarity variable, which is y by delta x, right. So, we had this. So, we are going to call this. So, we said eta. So, we are going to call this eta as a similarity variable, because that is what we are kind of using to scale up, you know, the velocity profiles at different x locations. So, what we are going to say is that similarity variable, okay, similarity variable, that is eta, right, which is equal to, so we said basically this is y by delta. Well, I mean, we do not know what, it's a function of that, right, something like that. So, now if you look at delta, okay, if you look at delta from 1, so we have got this, okay. Now, we are going to use this expression, okay, we are going to replace, you know, this delta x by this expression here, right. So, if I do that, what I will get is that, or eta is a function of y by delta is under root x of eta, okay. Okay, yeah, well, so we will write this as, this is under root, sorry, this is u infinity x of, or what am I doing wrong? No, y by delta x, yeah, that's fine, right. So, y by this, okay. So, y, yeah, u infinity, correct. So, it's fine. Now, what we are going to do is introduce, okay, introduce some sort of a factor, okay, so that we get an equality here. And what we are going to do is multiply this whole thing by 1 by under root of 2. That is, so that our eta becomes, right, eta is equal to y under root of u infinity 2x and nu, right, 2x and nu. And now, what is, why am I using this root of 2? What, from where did I sort of come up with this? You know, I multiplied this basically by a factor 1 by root 2. Well, the only reason for this at this point of time is that it helps in simplifying the differential equation, right, because this has been tried and tested. So, we kind of know from that, know from experience. So, that 1 by root 2, the factor with which we multiply, right, it just helps in, you know, simplifying the differential equation. Okay. All right. So, then we get a similarity variable, which is, as you can see, it's a function therefore of x and y, right, and you got the kinematic viscosity and the free stream, right. So, that seems like a, you know, good deal actually. Okay. So, now let us also define a stream function. Okay, so what we will do is we will define a stream function. Okay. Okay, and that stream function is x and y, which is equal to, right, 2 nu x u infinity okay, and a function of eta. Okay. Now, this f of eta, right, this f of eta is essentially the non-dimensional free stream function, stream function. Okay. So, f of eta is the non-dimensional or basically dimensionless, okay, non-dimensional stream function. That's the f of eta. So we've now got this stream function is this. Okay. So what is the usefulness of the stream functions? Well, stream function is basically we can get the velocity. So this in a 2D case, right? So stream function is basically one function, right? And using the same function, you can by differentiating the same function, you can get the two velocities. So in numerically, what happens is that you're basically solving from one function. Okay, that's the usefulness of it. So basically, what I'm saying is that u is del psi del x, right? And no, not del psi del x. It is del psi del y, right? So v is basically minus del psi del x. Okay, so that's how we get. So in this particular case, as you can see, the psi is basically a function of x eta, right, which again by itself is a function of x and y, and of course coefficient of kinematic viscosity in free stream. Okay, so if I were to do this here, so then this becomes del psi del eta, okay, into del eta del y, okay, which is equal to, okay, which is equal to del psi del eta, okay, is equal to x and f of dash eta, right, and del eta del y, del eta del y. Well, u infinity 2 nu x, right, if you were to look at this. So, this bit is basically calculus, right? This bit is calculus. So del psi del eta, so now psi is basically a function of eta, right? So here so psi is basically a function of eta. So when I say del psi so first what I need is del psi del y, right? Now since psi is a function of eta, okay, if I were to write it this, psi is a function of eta. So what I do here is, so del psi del eta and del eta del y. Okay. So now del psi del eta is nothing but this. So this bit. So this is the component. So this one is 2 this thing and f dash of eta. Okay. And del eta del y, so you can use this equation 2. So del eta del y. Okay. That's basically just u infinity to this. So it just boils down to this under root thing. Right. So if I do that, so now please remember that when I will just write stuff like f dash, f double dash. So all these differentials are basically with respect to eta. Now, so if I do this here, if you see, so 2 nu x, so 2 nu x. So therefore, what I get is that u is equal to, so then u infinity and u infinity, so that stays. So u infinity f dash of eta. This is a very important relationship. It's an extremely important relationship. So what do we understand from here? Let's just take a step back, okay? So what we wrote out here, we just came up with this similarity variable, which is given here in 2, okay? And then we said we're going to define a stream function in this fashion, right? So we define the stream, and okay, before I do that, so when I wrote down the eta here, right, I introduced this factor 1 by root 2, and I said this helps in the differential equation, okay. So I do that, and accordingly I come back and then I do write an expression for stream function, right, which is a function of x and y, and I get this, right. I have this, and from the stream function we use a stream function in order to basically we're going to solve the stream function. So then we get the velocity u, right, which is del psi del y, and we do the differentiation, right. And so of course, as you can see, the way I've chosen the stream function with the root 2 here, and the way I've chosen eta with the root 2 here kind of cancels out, it helps. Okay, so that's what we get, and so then finally what we get is that u is nothing but u infinity f dash eta. So now if I can solve for f of eta, which is the non-dimensional stream function, right, if I can solve for f of eta, I should be able to get u, right. So all I need here is f of eta, right, then I should be able to get the velocity components. Okay, so now so therefore let us go and look at the boundary layer equations. Now here, let us look at the first equation, which is u del x, right, plus v del u del y is equal to nu del 2u del y2. Okay. Now let's call these, this is the first term, right, this is the first term, this is the second term, right, and this is the third term. Okay. Now, so look at the first term. So we're going to look at term 1. Okay. So u del x. Okay. So what is u then? So what is u? So u is nothing but, using 3, right, it is u infinity f dash, right, is that fine? Okay, then it is del x of u, it is del x of u, okay. So which means that it is nothing but, so del x of u, so I'm going to write that, so del u del x, right, is basically equal to, because as you can see now that u is a function of eta, right. So then I can write del u del eta and del eta del x, right. So I can write that. So therefore I will write this as del eta, okay, of u. U again is u infinity and f dash, right, and del eta del x. Del eta del x, look at eta value. So this is the value of eta, right. So this is del eta del x. What will that be? Del eta del x. So x to the power minus half, right, x to the power minus half. So, basically then this becomes y u infinity 2 nu, okay, into minus half, right, minus half into right x of under root x, isn't it? So, if I am going to write it this way, so then what do we get here? So, therefore, if I do this, so then what I get is, okay, infinity square. Okay, so what we get here is, so then that is equal to, so this u infinity here in this here, so this can come out, so then this becomes u infinity square, okay, into f dash, okay, so that I get del del eta, so I get del del eta from here, right, okay, I'll write this, so it is basically del del eta, okay, let me write this better, I will write this cleanly, so then I get u infinity f dash into u infinity del f dash del eta, right, into y under root u infinity 2 nu minus 1 by 2 x under root x, x to the power minus, yes, because basically what I am writing here is, it is x, see it is 1, we are taking the derivative, we are basically taking the derivative of 1 by root x, or it is the derivative of x to the power minus half, right, which is equal to minus half and x to the power minus half minus 1, which is basically then again equal to minus half x to the power minus 3 by 2, right, which is nothing but minus half x to the power minus 1 into x to the power minus half. So, therefore, I wrote it like this, you know, it is just easier, that is all. So, minus half 1 by x and this, okay. So, then if I do this, so then what I will get is, so I am multiplying these two, so u infinity square f dash, and the del f dash del eta is nothing but a double dash, okay, f double dash, then we have a y, okay, we have a y, and let me sort of introduce this thing. So, I got u infinity 2 nu, and I am going to introduce this x over here into minus 1 by 2x, right. Now, y into u infinity by 2 eta x is nothing but eta, right, this whole thing is eta. This whole thing is eta. So, therefore, what we get is, this is equal to u infinity square f dash f double dash, okay, into eta into minus 1 by 2x, okay, minus 1 by 2x. So, basically what we are saying is, therefore, term 1, okay, so therefore, ultimately u del x is equal to minus, okay, u infinity square, okay, eta by 2x into f dash f double dash, right. So, what basically what I am doing here, okay, is that we have this set of equation, right. I have my equation, yeah, so this is my equation that I am trying to solve here, you know, this is the expomentum boundary layer equation. So, what I did here is, I transformed this first term here, in terms of the new variables, the non-dimensional stream function and eta, and the similarity variable that we've come up with, right. So, using that, so therefore, I am able to write that as eta and f dash and f double dash, right. So, similarly, what we will have to do here is do the same thing for term 2 and term 3, right. So, once we do that, so basically we get expressions, and then we will also transform the boundary layer equation, the boundary conditions, and then we will put all that together, right, and see what equation we get, and is it simple, or is it difficult to solve, or what is it, okay. So, I will do that. So, I have a little piece of a little code which I have written, and I will show you the output from there, okay. And hopefully, you should be able to write that up yourself and be able to do it, and it's quite fun actually, and all these things that we are discussing, okay, you begin to get those as plots, and I think that's very exciting when you see that. So, what I will do is I will stop here, and we'll finish this in the next 2 modules, and hopefully I'll have time in the next 2 modules itself to show you the actual plot from the computer code, right. So, which by the way I am using Scilab, if you are not aware of. I am using this because this is free, and I do not have MATLAB on my Mac. So, you can basically write this in whatever, you can use MATLAB if you have. Scilab is a free software. It is similar to MATLAB, but then the syntaxes are quite different. So, if you have a little bit of coding idea, you should be able to do it though. It's not too complicated. It's simple. So, the equation that we have is all these differential equations, right. And what is nice is that we kind of use this understanding, okay, of similarity. So, basically what we are saying is that since I can actually so basically what I am saying is that if I can solve for the u and v at location x1, I can just multiply those by a certain scaling factor, and I will get the velocities at x4. Hence this similarity principle. So, therefore, what I am using is a simple one variable. So, so basically what I am saying is I can use one variable to define the flow at x4 and x1, right. So, therefore, I write that. So, then I use this and this understanding, and therefore, I come up with this expression for delta x, and then we have eta we define as a new similarity variable, and another stream function, and then using the stream function, of course, we write u, right, and then that's all we need here. So, then we are just transforming this equation, the x momentum equation, into the similarity variable, So, to represent, these derivatives using the similarity variable, which we have done here. So, let us see what we get in the end when we also do it for 2 and 3, and also the continuity equation. So, we will do that in the next 2 modules. So, I will stop for now. Okay. Thank you.